Hey everyone, welcome back to Probability Theory. This will be lecture 17 of the course. And in this section, we're going to discuss a distribution that frequently is overlooked in a typical probability theory undergraduate course, but one that I think is worth looking at and just takes a minute also. And that's the negative binomial distribution. So let's go ahead and jump into it. And we'll call this section 2.6 the negative binomial distribution. And so the negative binomial distribution is really just a generalization of the geometric distribution. So the negative binomial distribution is a generalization of the geometric distribution. And I'll frequently abbreviate distribution like that just because it gets to be too much to write out. So let's talk through what they have in common first. So in the geometric and the negative binomial, what do they both have in common? Well, both of them have independent identical trials. Okay. They both have those. Okay, so no difference there. And for those trials, there are two possible outcomes. So two possible outcomes per trial, right? Okay, just like, remember the geometric, you can be either yes or no, or on or off, right? There's two options for each trial. The third thing they have in common then is the constant probability of success. So they also have constant probability of success. Now, where they differ is in the definition of the random variable. So in the geometric, remember, we define y to be the random variable that describes the number of the trial for the first success. The number of the trial for the first success, right? So remember that. So what's the probability that the first qualified candidate occurs on the third interview, for example? Right? So remember we did examples like that in the previous section. Now, what is the random variable then in the negative binomial distribution? So in the negative binomial, y is the random variable that describes the number of the trial for the rth success. The number of the trial for the, not the first, but the more general rth, RTH success. Okay, so example, find the probability that the first qualified candidate is on the we'll say fourth interview, right? So the first qualified candidate is found, I should say, on the fourth interview. This is geometric. But if I said instead, find the probability that the third qualified candidate is found on the fourth interview, this is negative binomial, right? So it's all about this first. Instead of first, we're saying something like third. Okay, and so that's why we say it's a generalization of the geometric distribution. The geometric distribution is really just a negative binomial distribution where the number of successes is set to 1. Okay. All right. We'll define the negative binomial in a second, but I want to give you one more example just to kind of set the stage here a little bit. So here's a nice example from the textbook. An exploratory oil well. An exploratory oil well drilled in a particular region. Should strike oil with probability 0.2. Should strike oil with probability 0.2. It's like a 20% chance of striking oil. Find the probability that the third oil strike comes on the 5th well drilled. Find the probability that the third oil strike comes on the 5th well drill. Okay, right, so you've got regions where you can drill oil wells, and they say the probability of striking oil with each drill is 20%. So let's find the probability that we drill 5 wells, and on the 5th well drill, we happen to find the third oil strike, right? And so what that means is you have these kinds of situations where you have strike, strike, no strike, no strike, strike. Right, so 1, 2, 3 out of 5, right? Or maybe you have no strike, and then you have 3 strikes in a row. Okay, so these would be examples of successful observations. Okay, and you can see there's going to be a range of these potential outcomes, right, that fit the bill. Here's one that doesn't fit the bill. Maybe you have a strike and then another strike, and then you have 3 non-strikes, and then you have the third strike on the 6th. So 1, 2, 3, 4, 5, 6. So that's not an example of a success, right? That's not a successful outcome. That's not a desired outcome. So these are the desired outcomes, and this one is not a desired outcome here. Okay, so let's test this. Let's just think about this. Let's think about the sort of the structure of this probability setup here. So first of all, do we have independent trials? Yep. Independent identical trials. All right, yeah, these are just in this case, the oil wells that are drilled. The drillings, we'll say. Right, and there's a series of them. There's a never-ending series, seemingly, at least theoretically, but we're interested in the ones that terminate with the third success upon the 5th drilling. Okay, and so for each drilling, there's 2 possible outcomes. So that's number 2. 2 possible outcomes, right? Either strike oil, yes or no. All right, so one of the 2 possible outcomes. Very good. And then, we're assuming constant probability here of success. 0.2. Right? Each drilling has a 20% chance of a success. Okay, and then now when we think about the random variable, right, what is y? What is the random variable here denoting? Well, it's the trial upon which we get the third oil strike. The trial upon which we get the third oil strike. Okay, and so this fits the pattern of a negative binomial distribution. Okay, we'll talk about what the probability function looks like here, but We denote this, we would say that y is negative binomial, and the parameters of interest here are the number of successes, which we'll use an R for, right? So in this case, the number of desired successes is 3, and the probability of success is the other thing we need, so 0.2. Right, so this one is negative binomial, and the parameters are R equals 3 and P equals 0.2. Okay. All right, so now let's go ahead and define the negative binomial. So what is the probability distribution look like? So a random variable y is said to have a negative binomial distribution. It's said to have a negative binomial probability distribution if and only if the probability of y is equal to y minus 1, choose r minus 1, right? So that familiar choose function, and then p to the r power times q to the y minus r power. Okay, and this is going to be true for all values of y that are equal to at least r, and then r plus 1, r plus 2, and so on. And then, of course, 0 less than or equal to p less than or equal to 1. Okay, and so this looks an awful lot like the binomial distribution, right? We just have different parameters in here, right? But this is obviously your probability of success. This is your probability of failure. This is the number of ways that these are the number of desired outcomes, right? So in the case of our striking oil 3 times in 5, striking oil for the third time on the 5th drilling, right? So it's important. It's not exactly binomial. It's negative binomial, right? But this counts the number of desired outcomes that fit the bill. And these are the probability of success. That's probability of failure. Now notice y here has to be at least equal to r. Well, r is the number of successes, so the number of trials has to at least equal the number of successes, right? So y here is the number of trials, and r is the number of successes. Okay, so that's what that's about. So what is our oil well probability then? Right. So what was our question? We said that y was negative binomial with r equals 3 and probability of success equal to 0.2, right? And what the situation was we were drilling oil wells, candidate oil wells, and each time we drill, we have a 20% chance of striking oil. And so the question was, what's the probability that we strike oil for the 3rd time on the 5th drilling? So we want to know the probability that y is equal to 5, right? So the 3rd success comes on the 5th trial. That's what basically we're saying here. This is equal to the probability that the 3rd success is on the 5th trial, okay, just in words, right? And so we know the probability distribution, right? It's y minus 1, choose r minus 1, and then p to the r power times the failure probability q to the y minus r power, right? So we can plug all these values in here. This is going to be 5 minus 1, choose 3 minus 1, times 0.2 to the 3rd power, and 0.8 to the 5 minus 3, so y minus r, 5 minus 3, so the 2nd power. Okay, so we have 4 choose 2 times 0.2 to the 3rd times 0.8 to the 2nd power. And you can do the math here. 4 choose 2 turns out to be 6. There's 6 different 6 desired outcomes, and they each have equal probability, and so 0.008 times 0.64. Multiply all that together, and you get 0.0307. So there's only a 3% chance that this will happen. So there's a 3% chance that our third oil strike occurs on our fifth drilling. Okay. All right. So that is the negative binomial. So you can see very clearly that this is a generalization of the geometric distribution. Remember, the geometric distribution would say something like, so in this case, GO and then P equals 0.2. And so the kinds of questions we can ask there is, what's the probability that our first oil strike occurs on the third drilling or something like that, right? And so this is the geometric, right? But it's just instead of saying the first success occurs on some trial, we say the rth success. In this case, the third success occurs on the fifth trial. So it's just a generalization, right? It's a loosening of the requirements. It's a loosening of the structure a bit. All right, very good. Let's do another example. This will be just like a card example. So let's say the probability of drawing a face card is something. The probability of drawing a face card from a 52 card deck is 12 in 52. Right, so that's approximately 0.2308. So let's find the probability that we draw 10 face cards with replacement and that the 10th is drawn on the 15th draw. So we want the probability of that we draw 10 face cards and the 10th occurs on the 15th draw. Okay, so I draw a card. It may or may not be a face card. I continue on, draw a second card. It may or may not be a face card. Each time I'm putting the card back in the pile, so this probability stays constant. Right? And what I'm saying is I want to know the probability that I draw 10 face cards in total and that the 10th one occurs on the 15th draw. Okay, and so in this case, our random variable y is going to track the number of the draw where we get the 10th face card, right? So this is going to be negative binomial, right? And r, the number of desired successes, is equal to 10. The probability of those successes is 0.2308. Right? It's very important that we say with replacement here, because obviously if we start pulling face cards out of this deck, then the probability of getting a face card is going to change, and we're no longer going to be dealing with a negative binomial distribution. The independent and identical trials is going to be fine, but the probability of success will change, and so you don't really have Bernoulli trials if that's the case. Okay, so that's why we're saying we're going to put the face cards back in. We're going to put the card, whatever we draw, we're going to put it right back in. So we want the probability that y is equal to 15. Right, let's remember the form of the distribution. It's y minus 1, choose r minus 1. And then it's p, the probability of success, raised to the r power, times q, the probability of failure, to the y minus r power. Right, and so for our case, we've got 15 is our sample size. That's how many things we're going to draw. So 15 minus 1, and then we want 10 successes of 10 minus 1. So 15 minus 1, choose 10 minus 1. And then our probability of success is 0.2308 to the r power, which is 10, And then our probability of failure is 1 minus 0.2308, which happens to be 0.7692. And that's going to be to the y minus r power, which is 5. In this case, so 10 minus 5 is 5. Okay, and you can work this problem out, and we get 14 choose 9, and then 0.2308 to the 10th power times 0.7692 to the 5th power. Now the 14 choose 10 can be simplified greatly, and you end up basically with 7 times 13 times 11 after you do all the cancellation. And then it's 0.2308 to the 10th power times 0.7692 to the 5th power. And all of this turns out to be equal to 0.000116. So very low chance of this happening. Okay. All right. Very good. And so that is the negative binomial distribution. And so just the last thing I'll say is the mean and the variance here. We won't prove this, but I'll just point it out. So if y is negative binomial with parameters r and p, r being the desired number of successes and p being the probability of success, then the mean is equal to the expected value of y, which is r divided by p. All right, so you take the desired number of successes, you divide it by the probability of success, and you get the mean. And the variance, sigma squared, the variance of y, is equal to r times 1 minus p, which is also known as q, divided by p squared. Okay, and so that is the variance, and this is the mean. Now remember, for geometric, so these are similar. So for geometric, we found that mu was equal to 1 over p, and we found that sigma squared was equal to 1 minus p over p squared. So obviously these have a lot in common. As we said, this is really just a generalization of the geometric distribution. So you could say that r is equal to 1 here, right? And that works in both places, right? So r is equal to 1, r is equal to 1. And so that's what's happening there. Okay, very good. I think that's where we'll leave it. Again, most classes will kind of gloss over that one. I like to teach that one just because I always like it when I can show students what a generalization looks like, and this is a very nice, simple to understand generalization of the geometric distribution. And it's also useful. I found that I've used it in real life, if you can believe it. So, all right, so we'll leave it there for now, and we will talk to you all next time. Take care.